Hi, my name is Sharina from the Institute of Flight System Dynamics at the Technical University of Munich in Germany. I am excited to present our latest research under the title Simulator-Based Mixed Reality Pilot Training, the Instructor Operator Station. As we embrace advanced air mobility and its promise of reshaping our airscapes with electric vertical takeoff and landing systems, short eVTOLs, a critical question emerges. How do we effectively train the pilots of the future for these novel aerial systems? Mixed reality technologies can support creating immersive and interactive training environments for aircraft following the Simplified Vehicle Operations concept, which require novel environments for practical and intuitive pilot trainings. The combination of real-world objects such as switches, buttons, joysticks, and seatbelts with virtual elements like virtual environments, aircraft 3D models, and overlays enables a more comprehensive sensory experience. Pilots can physically interact with a mixed reality simulator cockpit and its instruments, such as in a real aircraft. With overlays, different training scenarios can be adapted according to the individual learning levels of trainees. Despite this potential, regulatory guidelines by EASA or FAA for simulator-based eVTOL pilot training, especially concerning the Instructor Operator Station design, are nascent and require substantive development. This figure highlights the role of the instructor within the system. By featuring audio-visual communication and instant feedback loops, we illustrate the system's capacity for real-time responsiveness, which is crucial for maintaining engagement and ensuring that the training objectives are met effectively. As highlighted in green, the instructor has to brief, explain, guide, monitor, evaluate, and debrief the pilot while still controlling the simulator and monitoring the overall system. Our paper explores the role of the instructor operator in a mixed reality simulator setup. It identifies the need to evaluate 2D instructor tools, such as those provided by mixed reality headset manufacturer Varjo, highlighting a research gap in assessing these tools and their effectiveness in training scenarios. For this, a usability evaluation of these tools as part of an existing mixed reality flight simulator setup in the form of a small-scale qualitative user study is presented. The study engaged a total of 7 male subjects, all with experience tutoring in a university module that utilizes a fixed-base simulator for the Diamond DA-42, a twin-engine fixed-wing aircraft. All participants were well acquainted with both the mixed reality simulator setup and the pilot's perspective, so everyone knew how to operate the eVTOL. The flight simulator training device in this paper refers to a motion-based mixed reality full-flight eVTOL simulator for a generic single-pilot eVTOL system with a powered lift flight and a wing-borne flight configuration. The simulator itself is located at the Institute of Flight System Dynamics at the Technical University of Munich in Germany. It consists of 3 interconnected environments: the immersive mixed reality training environment, the motion-based mixed reality eVTOL flight simulator, and the Instructor Operator Station. The immersive mixed reality training environment includes the virtual environment and augmented reality overlays, and spatial and communications audio. This environment is integrated into the simulator and can be adjusted to suit the pilot's needs. The motion-based mixed reality eVTOL flight simulator incorporates a 6 degrees of freedom motion platform, a complete cockpit with control elements, a mixed reality headset, here the Varjo XR3, and a headset for communication and simulated aircraft and environment sounds. An instructor on the ground is situated at the Instructor Operator Station, which is running Varjo base. The Instructor Operator Station also allows instructors to control the simulator and the simulation or intervene in case of emergencies. However, for this study, participants only worked with audiovisual communication tools, such as the headset and Varjo base. Internal functions of Varjo base include showing and recording the pilot's perspective, eye tracking, hand tracking, and a pointer function. While the immersive experience was generally praised for its authenticity, participants pointed out areas needing refinement, such as the need for a wider visual field of view and more stable interaction tools to enhance the training effectiveness. Eye tracking and audio cues were particularly noted for their ability to augment situational awareness and immersion, proving crucial for real-time training and debriefing sessions. However, the challenge of maintaining pointer stability amidst rapid pilot movements called for improved control mechanisms. So when the head moves, then the view moves too. Instructors appreciated the mixed reality setup for offering diverse perspectives, including fixed and external views, though they expressed a desire for seamlessly integrating multiple viewpoints to avoid potential disorientation. A notable point was the mixed reception towards the instructor operator's physical setup. While the digital tools provided through mixed reality were recognized for their utility, there was a sentiment of missing the direct tactile interaction available in conventional simulators, underscoring a need for a balance between digital innovation and the intuitive aspects of physical controls. Participants proposed enhancements such as dual controls for a more interactive teaching experience and additional augmented reality content to tailor the training more closely to individual learning needs. The consensus underscored the transformative potential of mixed reality in pilot training, with suggestions for iterative development focusing on enhanced interactivity, user-friendly interfaces, and a deeper integration of physical and digital training elements to fully leverage the technology's capabilities. In a bottom-up approach, the results of the user study lead to the identification of performance-shaping factors of an instructor in a mixed reality eVTOL flight simulator setup in this context. For complex systems such as eVTOL aircraft and flight simulator training devices, it is necessary to describe related performance-shaping factors in a systematic way. An efficient method to describe the dependency of complex influences is the fault tree or event tree, used in various disciplines such as computer science, linguistics, and mathematics. The VDI 4006 standard, page 1, is used to provide a versatile baseline for further event tree and fault tree analysis of future mixed reality pilot training concept. This standard describes the fundamental knowledge about the interrelationships of man and machine to increase the reliability and safety of the man-machine system. This relates primarily to the human-centered design of technical equipment in Germany. It also addresses various training and educational aspects. In addition, methods are introduced to discover processing needs and weaknesses as well as the validation of the measures taken. This can be directly applied to enhance mixed reality environments for more effective flight training in flight simulator training devices by considering human factors in the design and evaluation of these systems. The performance-shaping factors relevant regarding mixed reality training are highlighted in light green. They can be categorized into external factors like organizational and technical requirements and internal factors such as the instructor's personal capabilities and motivation. The Instructor Operator Station design, particularly its ergonomic aspects and intuitive control placements, emerges as a vital component in the supporting of the instructor's role, ensuring the ability to effectively monitor and guide pilots through varied and complex training scenarios. In the discussion, our analysis combines insights from both the user study and the identified performance-shaping factors, focusing on the intricate role of instructors in mixed reality flight simulator training devices for eVTOL aircraft. Key points include task difficulty and communication. The limited cockpit space in eVTOL aircraft necessitates mixed reality tools for communication. The Vario XR3 enhances realism, but sometimes restricts the field of view, affecting task difficulty and the instructor's ability to monitor pilot actions. Physical and psychological demands. The need for instructors to continually adjust interactive tools like pointers due to pilots' movements highlights the significant physical and psychological demand placed on them, impacting their ability to maintain focus and detect errors. Ergonomic design and instructor position. The Instructor Operator Station design and the position impact the instructor's effectiveness, pointing to the need for ergonomic enhancements and additional input methods to support the instructor's role more effectively. Human-centered design in augmented reality. Emphasizing intuitive augmented reality features that allow instructors to highlight key information and incorporating feedback mechanisms for debriefing sessions are essential for aligning with human-centered design principles. The interplay between the performance-shaping factors and practical findings from the user study indicate the importance of a balanced approach to improving mixed reality technology for pilot training, focusing on both instructor support and system design enhancements. To conclude, we summarize our findings in a list of essential and recommended features for a mixed reality instructor station, tagged by their current availability in commercial products like those provided by Vario, and those yet to be developed. So currently available through Vario or Vario Base are a realistic field of view and headsets essential for immersive training, an interface providing instructors a pilot's perspective crucial for accurate guidance, advanced eye tracking, boosting situational awareness and enabling interactive learning, audio feedback integrated into the mixed reality system, vital for recognizing errors and enhancing immersion. Also, control over simulator and aircraft settings, allowing tailored training experiences. Additionally, debriefing tools to review and improve pilot performances based on past maneuvers. Looking ahead, we recommend developing a stabilized pointer tool to counteract the effects of rapid head movements, ensuring precise instruction, hybrid camera views that merge multiple perspectives, offering a more complex view of the pilot's environment, as well as customizable augmented reality instructions to adapt training to various phases and styles, multi-pilot monitoring capabilities, increasing training efficiency by handling multiple trainees at once, and last but not least, automated feedback systems that provide real-time, individualized feedback, significantly enhancing the learning process. As we move forward, the goal is to refine these mixed reality training environments, ensuring they are effective, efficient, and adaptable to the fast-paced advancements in aircraft technology, thereby equipping the next generation of pilots for the challenges and opportunities of tomorrow's skies. Thank you very much.